Welcome to this deep dive, where we're tackling a fascinating subject, the Earth's interior.
It really is. Kind of the engine room of our planet, isn't it?
Exactly. Driving everything from, mountain building to volcanoes. Today, we want you to feel like you're right here with us, sort of figuring this out with an expert.
Like a study session almost.
Yeah, perfect.
Mm.
So we'll explore how we even know it's down there, the whole story of earthquakes, what causes them, their effects, then the Earth's layered structure, and finally, volcanoes and the landforms they create. Ready to dig in?
Absolutely. It's a journey into well, the unseen, but it shapes everything on the surface. So where should we start? How we get the info?
Sounds good. Let's start there. How do we piece together this puzzle of the Earth's insides? It feels like trying to understand an onion without actually peeling it back all the way.
That's a really good way to put it. We start with what we can, directly observe or touch.
Like rocks on the surface.
Exactly. Surface rocks give us clues. Then there's mining. We can go down a few kilometers. Those deep gold mines in South Africa, for instance, they reach about 3 to 4 kilometers. We get actual samples.
Okay, 3 to 4 kilometers. That's deep, but the Earth is much deeper, right?
Oh, much deeper. So then we have deep drilling projects. Things like the Deep Ocean Drilling Project or the Kola Deep Borehole in Russia, which actually went down to 12 kilometers. That gave us more direct material.
12 kilometers, that's impressive. Still just scratching the surface, though, relatively speaking.
Pretty much. And volcanic eruptions also bring up material magma, which becomes lava. We can analyze that in labs.
But do we know exactly where that magma comes from deep down?
That's the tricky part. The depth is often uncertain. So, yeah, direct sources are valuable, but limited. They don't get us deep enough for the full picture.
Right. So if direct glimpses are limited, what about the indirect methods? How do those give us the broader view?
Okay, this is where it gets really clever, I think. We look at the properties of matter. We know temperature, pressure, and density all increase significantly as you go deeper.
Okay.
So by estimating the rate of that increase and knowing the Earth's overall size, we can calculate approximate conditions at different depths.
Yeah, makes sense. What else?
Well, then there are meteors.
Meteors, how do they help?
The idea is that they formed from similar stuff as the early Earth. So studying their structure and composition gives us hints about what our planet might have been made of initially.
Interesting connection.
Yeah. And then there's gravity. The force of gravity isn't exactly the same everywhere on Earth.
Really? Why not?
It's slightly stronger at the poles and weaker at the equator, mainly because the Earth bulges a bit. But there are also smaller variations called gravity anomalies.
And these tell us?
They indicate differences in the mass of material in the crust below. Denser rock, more gravity. Also, magnetic surveys help map out magnetic materials.
Okay, so gravity and magnetism give clues about the crust. But you said there was one method that's maybe the most important.
Yes. Seismic activity. Earthquakes.
Right, the waves they send out.
Exactly. Studying how those earthquake waves travel through the Earth, where they speed up, slow down, change direction, or even disappear. That's our single best tool for mapping the interior.
It sounds like using sound waves almost to see inside.
It's a very similar principle, yes. Analyzing those wave patterns tells us an incredible amount.
Okay, quick recap then. Direct evidence. Surface rocks, deep mines, drilling, volcanoes useful but shallow. Indirect. Analyzing temperature, pressure, density increases, looking at meteors, mapping gravity and magnetic fields, and crucially, tracking earthquake waves. It really is like planetary detective work.
You've got it. That's the toolkit.
So let's dive deeper into these earthquakes then. What exactly is happening when the ground starts shaking?
Fundamentally, an earthquake is the Earth releasing energy. This energy has usually built up as stress along a fault.
A fault being like a crack in the rock.
Essentially, yes. A sharp break in the crustal rocks. Rocks on either side of the fault are trying to move, but they get stuck because of friction.
Okay, locked together.
Right. But the pressure keeps building. Eventually, the friction is overcome, and the rocks suddenly slip past each other. Bang! That sudden movement releases energy in the form of seismic waves.
And that's the shaking we feel.
That's the shaking. Now, the point inside the Earth where that energy release actually happens, that's called the focus, or hypocenter.
Okay, the starting point.
And the point directly above the focus, right on the surface, that's the epicenter. That's usually where the waves arrive first, and the shaking is strongest.
Focus underground, epicenter on the surface. Got it. So this released energy travels as waves. What kinds are there?
Right, seismic waves. We broadly group them into 2 types, body waves and surface waves.
Body waves travel through the Earth's body, I assume.
Precisely. They originate at the focus and travel through the interior. There are two kinds of body waves, P waves and S waves.
P and S, what's the difference?
P waves stand for primary waves. They're the fastest. They arrive first at seismic stations. Think of them like sound waves. They compress and expand the rock as they go, moving parallel to the direction the wave is traveling.
Okay, push-pull waves. And they travel through.
Solids, liquids, and gases. They can go pretty much anywhere inside the Earth.
Okay. And S waves?
S waves are secondary waves. They arrive later because they're slower. Their motion is different. They shake the ground perpendicular or side to side relative to their direction of travel. Imagine shaking a rope up and down.
Like a wave on a rope. Okay. And the key thing about S waves?
The crucial thing is, S waves can only travel through solid material. They cannot pass through liquids or gases.
That sounds really important for figuring out the interior structure.
It's absolutely critical. That single property of S waves is key evidence for the state of the Earth's core.
So P waves are fast, go anywhere, push-pull. S waves are slower, solids only, side to side. What about the surface waves you mentioned?
Right. When the body waves, P and S, reach the surface, they interact with the surface rocks and generate surface waves. These travel along, well, the surface of the Earth.
Are they faster or slower?
Generally slower than body waves. But, and this is important, they are often the most destructive.
Why is that?
Because their motion is more complex, kind of rolling or swaying, and it happens right where buildings and infrastructure are. They cause the most ground displacement and damage.
Okay, so body waves tell us about the deep interior. Surface waves cause the most damage up top. Now, how do these waves behave as they travel? Do they just go straight?
Not quite. Their speed depends on the density of the material they're passing through. Generally, the denser the material, the faster the waves travel.
So they speed up as they go deeper?
Typically, yes, because pressure increases density. But if they hit a boundary between different layers, say between the mantle and the core where the density changes abruptly, their speed changes and their direction can change.
How does the direction change?
They can be refracted, meaning bent, like light passing from air into water. Or they can be reflected, bouncing off the boundary like light off a mirror.
So studying these bends and bounces helps map the layers.
Exactly. It's by tracking these speed changes, refractions, and reflections that seismologists have figured out where the boundaries between the crust, mantle, and core are.
And does this connect to those shadow zones I've read about? Areas where waves don't show up?
Precisely. Shadow zones are fascinating. They are regions on the Earth's surface where seismographs don't detect certain waves from a specific earthquake.
Why would they disappear?
Okay, picture an earthquake. Seismographs located within about 105 degrees of angular distance from the epicenter record both P and S waves clearly.
Right. Close by, you get both.
But beyond 105 degrees, something changes. S waves just vanish. They aren't recorded directly at seismographs beyond that 105-degree mark because they hit the liquid outer core. Since S waves can't travel through liquid, the outer core casts a huge shadow for S waves, covering more than 40% of the Earth's surface from any given earthquake.
Wow. So the S-wave shadow zone is direct proof of the liquid outer core. What about Q waves?
P waves are different. They can go through the liquid core, but they get bent, refracted quite strongly when they enter and leave it. This bending creates a ring-shaped P-wave shadow zone, typically between 105 degrees and 145 degrees from the epicenter, where direct P waves are absent or very weak.
So the S-wave shadow is bigger because they're stopped completely, while the P-wave shadow is due to bending.
You've got it. The absence and bending of these waves is incredibly revealing about the deep Earth's state: solid mantle, liquid outer core, solid inner core.
That is an amazing piece of scientific deduction. Incredible. Now, are all earthquakes caused by tectonic plate shifting, or are there other types?
Tectonic earthquakes from movement along faults are definitely the most common and usually the biggest, but no, there are others.
Such as?
You can have volcanic earthquakes, which are linked to magma movement under active volcanoes. They're usually smaller and localized.
Okay.
Then there are collapse earthquakes. These are minor tremors caused by, say, the roof of an underground mine or cavern collapsing.
Makes sense.
Explosion earthquakes can be caused by, well, large explosions like nuclear tests or massive chemical blasts. And sometimes building large reservoirs can trigger earthquakes.
How does a reservoir cause an earthquake?
It's called reservoir-induced seismicity. The sheer weight of the water in a large reservoir can increase stress on faults underneath, potentially triggering small to moderate earthquakes.
Okay, so different triggers. Now, how do we measure them? We always hear about the Richter scale.
Right. The Richter scale was an early way to measure magnitude. Magnitude measures the energy released at the earthquake source, the focus.
So it's about the power of the quake itself.
Exactly. Modern magnitude scales are logarithmic. This means each whole number step up, say, from a 5 to a 6, represents about a 10-fold increase in the measured wave amplitude and roughly a 32-fold increase in the actual energy released.
So a magnitude 7 is way, way more powerful than a 6.
Hugely more powerful, yes. But then there's intensity.
Intensity, how's that different?
Intensity measures the effects of the earthquake at a specific location. What people felt, the damage done to buildings, landscape changes. We use scales like the Modified Mercalli Intensity (MMI) scale for this.
And that goes from...
It typically ranges from I not felt to 12. Catastrophic destruction. Intensity depends not just on the magnitude, but also your distance from the epicenter, the local ground conditions like soft soil versus hard rock, building construction.
So a high magnitude quake far out at sea might have low intensity on land, while a moderate magnitude quake right under a city could have very high intensity.
Precisely. Magnitude is one number for the source. Intensity varies with location and impact.
Got it. Magnitude energy released. Intensity observed damage. Now, let's talk about those effects. What are the immediate dangers?
Well, the most obvious is ground shaking itself. It can range from a gentle rumble to violent jolting that causes structures to collapse.
Yeah.
Then there's differential ground settlement, where the ground sinks unevenly, cracking foundations. Landslides and mudslides are very common in hilly areas.
And liquefaction, I've heard that term.
Soil liquefaction, yes. It happens in loose, water-saturated soils. The shaking makes the soil behave like a liquid, losing its strength. Buildings can sink, tilt, or even collapse.
Scary. What else?
Ground lurching or cracking, avalanches in snowy mountains, ground displacement along the fault line itself. If dams or levees fail, you get major floods. Fires are a big hazard, too, from broken gas lines or electrical shorts.
And tsunamis?
Yes, if a large earthquake happens under the ocean floor and displaces a lot of water, it can generate devastating tsunami waves that travel across entire oceans.
It's a truly formidable list of hazards. So, recapping earthquakes, sudden energy release along faults, P waves, fast, all media, S waves, slower, solids only, surface waves, destructive. Shadow zones reveal the liquid outer core. Different types exist. Magnitude measures energy, intensity measures damage. And the effects are wide-ranging and potentially catastrophic.
So that covers the key aspects well.
Okay, so all this seismic detective work, analyzing these waves, has allowed us to build a picture of the Earth's structure. Can you walk us through the main layers?
Absolutely. Based heavily on seismic wave velocities, we've identified three main concentric shells. The crust, the mantle, and the core.
Let's start at the top, the crust.
The crust is the outermost, thin, solid, and relatively brittle layer we live on. But it's not uniform. There's oceanic crust and continental crust.
What's the difference?
Oceanic crust, under the oceans, is thinner, averaging only about 5 kilometers thick. It's also generally denser and younger. Continental crust, making up the land masses, is much thicker, averaging around 30 kilometers, but it can be up to 70 kilometers thick under major mountain ranges like the Himalayas.
So, thin and dense under oceans, thick and less dense for continents. What's beneath the crust?
Beneath the crust lies the mantle. This is a much, much thicker layer, extending down about 2,900 kilometers from the base of the crust.
Is there a sharp boundary?
Yes, the boundary between the crust and the mantle is called the Mohorovičić discontinuity, usually just shortened to the Moho.
The Moho, okay. And the mantle itself, is it uniform?
No, it also has layers. The uppermost part of the mantle is solid and rigid, and together with the crust, it forms the lithosphere. This is the rigid outer shell that's broken into tectonic plates.
Lithosphere, crust, plus top of mantle.
Right.
Below the lithosphere, extending down to about 400 kilometers or so, is a zone called the asthenosphere. Astheno means weak.
Weak? How so? It's not liquid, but it's partially molten, or at least very close to its melting point, and behaves plastically. It can flow very slowly over geological time. This is the layer the tectonic plates ride on, and it's the source region for most magma.
Ah, so the weak layer allows plate movement and generates magma. What's below the asthenosphere?
Below the asthenosphere is the lower mantle. This extends all the way down to the core and is believed to be solid due to the immense pressure, even though it's very hot.
Okay, so crust, then lithosphere, crust plus rigid upper mantle, then the plastic asthenosphere, then the solid lower mantle. What about the very center, the core?
The core starts at the 2,900 kilometers depth at the boundary with the mantle, and again, seismic waves tell us it has two parts.
Which are?
The outer core, extending from 2,900 kilometers down to about 5,150 kilometers, is liquid.
And we know it's liquid because...
Because S-waves cannot pass through it. That S-wave shadow zone is the key evidence.
Right, got it. And inside the liquid outer core?
is the inner core, from 5,150 kilometers down to the Earth's center at about 6,370 kilometers. Despite being even hotter than the outer core, the immense pressure forces it to be solid.
Solid inner core, liquid outer core, what are they made of?
Primarily iron and nickel, very dense metals. Geologists sometimes call the core the knife layer, from the chemical symbols Ni for nickel and Fe for iron.
Knife, okay. And this metallic core is important for something else too, right?
Yes, the motion within the liquid iron outer core is believed to generate the Earth's magnetic field through a process called the geodynamo. That field protects us from harmful solar radiation.
It's amazing how it all fits together. The structure dictated by how waves travel, leading to this layered planet with a magnetic shield. Just to quickly recap the structure. Thin crust, Oceanic Continental, thick mantle, rigid lithosphere on top, plastic ionosphere below, solid lower mantle, and the core, liquid iron outer, solid iron nickel inner.
An excellent summary.
Now let's shift focus to the more dramatic surface expressions of this internal heat volcanoes. What defines a volcano?
Simply put, a volcano is a vent or opening in the Earth's surface through which molten rock, gases, and debris erupt.
And the molten rock, it's magma below ground and lava above, right?
Exactly. Magma is the molten rock while it's still within the Earth, usually originating in the astinosphere, or lower crust. Once it erupts onto the surface, we call it lava.
What makes a volcano active?
Generally, an active volcano is one that is currently erupting or has erupted in recent recorded history and is expected to erupt again.
And it's not just lava flowing out, is it? There's often ash and gas, too?
Oh, yes. Eruptions release a mix of materials, lava flows certainly, but also pyroclastic debris that includes rock fragments, larger chunks called volcanic bombs that fly through the air, and finer particles like ash and dust, and significant amounts of gases, water vapor, carbon dioxide, sulfur compounds, nitrogen, and others.
We see volcanoes in all sorts of shapes and sizes. Why the variety? Like those gentle slopes in Hawaii versus steep cones like Mount Fuji?
The shape and eruption style depend heavily on the type of magma, particularly its viscosity, or resistance to flow, and its gas content.
Okay, so different magma, different volcano.
Largely, yes. Let's look at the main types. Those broad, gently sloping volcanoes, like in Hawaii, are called shield volcanoes.
Like a warrior shield lying flat.
Exactly. They're built up by layers of very fluid, runny basaltic lava. Because the lava flows easily for long distances, it creates wide, low-profile cones. Eruptions are usually effusive, meaning relatively gentle lava flows, unless water gets into the vent, which can cause steam explosions.
Okay, fluid lava makes shield volcanoes. What about the steep ones?
Those are typically composite volcanoes, also called stratovolcanoes. They're built from alternating layers of more viscous lava flows, like andesite or dacite, and pyroclastic deposits, ash, bombs, rock fragments.
Viscous means thicker, less runny lava.
Right. Because it's thicker, it doesn't travel as far, building steeper slopes. Also, the thicker magma traps gases more easily, leading to more explosive eruptions that throw out lots of pyroclastic material. Think Mount St. Helens or Vesuvius.
Explosive eruptions, layers of lava, and ash composite volcanoes. Then there are calderas. They look like huge craters.
Calderas are formed by the most violent type of eruptions. The eruption is so massive it empties a significant portion of the underlying magma chamber. Without that support, the ground above collapses inward, leaving a large depression or caldera.
So the volcano essentially collapses into itself.
In essence, yes. Crater Lake in Oregon is a famous example where a caldera has filled with water.
Wow. I've also heard about huge flat areas covered in lava, like the Deccan Traps in India. They don't look like typical volcanoes.
Those are flood basalt provinces. They're formed by immense outpourings of extremely fluid basaltic lava, not usually from a central cone, but from long fissures or cracks in the crust.
So lava just floods out over vast areas.
Yes, covering thousands, sometimes millions, of square kilometers with thick sheets of basalt. These are some of the largest volcanic events known on Earth. The Deccan Traps are a classic example.
And what about volcanoes under the sea?
Those are primarily mid-ocean ridge volcanoes. They occur along the extensive mid-ocean ridge system, the underwater mountain range where tectonic plates are spreading apart. New oceanic crust is formed here through frequent, typically non-explosive eruptions of basaltic lava onto the seafloor.
Okay, so a real spectrum. Gentle shield volcanoes, explosive composite cones, catastrophic caldera collapses, vast flood basalts, and the continuous activity at mid-ocean ridges. That covers the surface features. What about the landforms created when magma doesn't reach the surface, the intrusive ones?
Right, intrusive or plutonic landforms. These are bodies of igneous rock formed when magma cools and solidifies within the Earth's crust. They only become visible if the overlying rock is eroded away.
Like what?
The largest are batholiths. These are huge, irregular masses of cooled magma, often granitic, that represent solidified magma chambers deep in the crust. They can cover vast areas.
Giant underground blobs of granite, basically. What else?
Laccoliths are somewhat smaller. They form when magma pushes up between layers of rock, bowing the overlying layers into a dome shape. They often have a flat floor.
So they make a sort of underground bulge.
Exactly. Then you have lapilliths, which are saucer-shaped intrusions, concave upwards. Phacoliths are lens-shaped bodies that often form in the crests or troughs of folded rock layers.
Okay, those names are a bit technical. Lapolith, like a sagging saucer. Phacolith, like a lens in folds. What about sills and dikes? Those seem more common.
Yes, they're sheet-like intrusions. Sills are formed when magma squeezes between existing rock layers, running parallel to them. They're like horizontal sheets. If they're very thin, they might be called sheets instead of sills.
Okay, parallel sheets are sills and dikes.
Dikes cut across the existing rock layers. They form when magma fills vertical or near-vertical cracks or fissures. They look like walls of igneous rock cutting through the surrounding rock. They often act as feeders for surface eruptions.
Wall-like cross-cutting features are dikes. It's amazing how many shapes magma can take when it cools underground.
Yeah.
Just to recap volcanoes quickly, they're vents for magma, lava, ash, gas. Types include shield, composite, caldera, flood basalt, mid-ocean ridge, based on lava and eruption style. Intrusive forms are cooled magma bodies underground, like batholiths, laccoliths, sills, and dikes.
You've covered the main points perfectly, and you can see how it all connects. The internal heat drives mantle convection, which moves plates, causing earthquakes and forming magma that erupts as volcanoes or cools underground.
It really paints a picture of a dynamic, interconnected planet driven by forces deep beneath our feet. Understanding these processes, from seismic waves to volcanic plumbing, isn't just academic, is it? It helps us grasp the hazards and resources of our world.
Absolutely, it's fundamental physical geography.
So as we wrap up this deep dive into the Earth's interior, maybe something for you to think about is this. How does knowing about the liquid outer core or the source of magma not only help us, say, predict earthquake shaking or volcanic hazards, but also guide our search for geothermal energy or mineral deposits, and even inform how we think about the evolution of other planets?
That's a great question to ponder. It connects this knowledge to broader scientific and societal issues.
Exactly. It's a thought to carry with you. Thank you for joining us on this exploration beneath our feet. Keep exploring.